right. So, it is called forward stage wise selection, where at each stage you do the following, okay. Or let me rephrase that. On the first stage you do the following. So, you pick the variable that is most correlated with the output, okay. Pick the variable that is most correlated with the output, and then you regress the output on that variable, okay. Find the residual. Okay. Now what you do is pick the variable that is most correlated with the residual, okay. Regress the residual on that variable, okay. Now add it to your predictor, okay. So what is your predictor? You already had one variable, right, then you had a coefficient for that variable which you got by the first regression. Now you have a second variable and you have a coefficient for that variable which you got by regressing the residual on this variable. So essentially what you are trying to do is, okay, the first variable makes some prediction, okay, the second variable is going to try to predict what the error is, right. So essentially now I will be adding the error to the prediction of the first variable. Did that make sense, right. So the first variable, let us say that that is the true output that I want, right. So the first variable will make a prediction saying that, okay, this is the actual fitted value, right, and this is the residual, right. What I am trying to do with the second variable is actually to predict this gap, right. So when I add the second variable with this coefficient to the first variable, so what I am essentially doing is, okay, the first variable will give this as the output, the second variable will make some other prediction, let us say that much, so I will add the two, so the new output will be that, right. Now I still have a residual left, right. So then I will pick a third variable which is maximally correlated with this residual, and now I add the output of all the three, okay, and then I get my new predictor, right. Does it make sense? So at every stage I find the residual, whatever has not been predicted correctly by the previous k stages, right, whatever is the residual error after the previous k stages, and try to predict that using the new variable. And essentially I find the direction which is most correlated with this prediction, and then I try to give you that, okay. Make sense, right. This is called forward stage wise selection, right. So what is the advantage of stage wise selection? Come on, I asked a question, I believe. Can you think of any advantage of this? Sorry?
You are not randomly picking a variable.
Neither was I randomly picking a variable in the previous methods, right. I was picking greedily, that was not random.
At least you are approaching towards a solution like before.
No, even in the previous case I only picked variables that gave me better fits, right. In fact I will tell you that it will probably converge faster in forward stepwise selection rather than forward stage wise, okay. But there is another significant advantage here. If you just thought about the process of fitting the coefficients, at every stage I do a univariate regression, right. At every stage I am just regressing the residual on one variable, right. Every stage it is a univariate regression, right. In forward stepwise selection, so every stage I will add a new variable, but then I have to do a multivariate regression, I have to do the regression all over again. I am not able to reuse the coefficients from the previous step, right. So when I add a new variable, I basically now I have k plus 1 variables and I do a new regression with k plus 1 variables. But in this case what is happening, at every stage I just have to do a linear regression, I keep all the work that I have done so far intact. So in fact since we are doing this only one at a time, right, I am not, even though I might have k variables in the system, right, but the coefficients I have for the k variables might not be the same k coefficients I would have gotten if I had started with this k variables and did a linear regression on it, okay. So the coefficients could be different, right. If I take those k variables and do linear regression, I will get a better fit rather than doing this stage wise fit, but we prefer to do the stage wise fit because it saves us a lot of computation. Make sense? So eventually everything will catch up and you will get the same kind of prediction at the end of it, but you might end up adding a little bit more more variables in this work, in this approach, but that is fine. Right. Was that a question? Okay. So the next class of methods we will look at are called shrinkage methods, where the idea is to shrink some of the parameters to 0, shrink them towards 0, right. So in the subset selection we are essentially, if you think about what we are doing, all this variables or all the variables that we did not select, we are setting the coefficients to 0, right. But instead of doing an arbitrary greedy search or stage wise selection and so on and so forth, in shrinkage methods what we do is we come up with a proper optimization formulation, right, which allows us to shrink the unnecessary coordinates. Okay. Ideally we would like to shrink them all the way to 0, but there are problems in doing that, but we will try to keep them as small as possible. You can do some post processing and then get rid of really small coordinates and things like that, but we will really like to shrink these coordinates, right. So this is fine from the prediction accuracy point of view, right. From the interpretability point of view, it still leaves a little bit to be desired, because you might have a lot of coefficients with a lot of variables with very small coefficients, right, in the system. So it is still a little bit of a thing, but mathematically this is a much sounder method than any of these things we have been talking about. And of course this is the soundest, but also impossible. Right. So the first thing we will look at is called ridge regression. So the whole idea behind all of this shrinkage methods is that you are going to have your usual objective function, which is what? The sum squared error, right. You are going to try and minimize the sum squared error. In addition, you are going to impose a penalty on the size of the coefficients, right. So you want to reduce the error, but not at the cost of making some coefficient very large, right. In fact, you are going to try and shrink the coefficients as much as possible. So what will happen is your optimization procedure will try to find solutions which have as small a coefficient as possible and give you the similar kind of minimization in the squared error objective. Okay. It's okay, I will waste that much of the board, I will write things here. So what is your normal objective function? Right. So that is a normal objective function for finding the betas, right. So your beta hat is essentially this. Right. So now what I am saying is, hey, let us not do this, but let us do this with a constraint, right. So what is a constraint? okay, fairly straightforward. I have added a squared norm constraint, right. So, I am just saying that, okay. So, this is essentially the, think about it, this is L2 norm for my this thing. So, so taking the root, I am just leaving it as a square, does not matter, right. So, it is just like an L2 norm constraint for my data. So, I can make this into an unconstrained problem, right. Okay. Of course, lambda has to be greater than 0. Why do I want the betas to be small? Okay, good question actually. So, what we wanted to do was to make sure that you are reducing the variance of your model, right. So, that is essentially what we are trying to do now. All the subset selection was, if we set the coefficient to 0, we said you have lot fewer parameters to estimate, right. So, now what I am doing, if I am by imposing the size constraint on the parameters, right, the size constraints on the variables, I am actually reducing the range over which these variables can actually move around, okay. So, if you think about it, if I have moderately correlated input variables, okay, or correlated or anti-correlated input variables. So, let us say I have two variables which x1 and x2 which are correlated, okay. Now, I can have a large beta 1 and a large negative beta 2, okay, that essentially will cancel out each other in terms of the predictions I am making, because x1 and x2 are themselves correlated, right. So, I can actually make my beta 1 very large and my beta 2 largely negative, right. So, that it will just cancel out the actual effects of the two variables, right. So, it essentially becomes a difference of beta 1 beta 2 that actually matters, right, not necessarily the difference in magnitude of beta 1 beta 2 that matters, not the actual values. So, in which case, so I can basically have a large class of models which will give me the same exact output, right. So, this makes my problem much harder to control, and then that increases the difficulty of the estimation problem, right. By now saying that no, I can't allow these things to become very large, okay, then I am restricting the class of models I am going to be looking at. Okay, so that is the reason why restricting the size of beta helps. Yeah, I did not explain this completely last time, so thanks for asking the question, right. So, so we just have to make sure that our lambdas are positive, we know that. So, Lagrange multipliers have to be positive and so on and so forth. So, now I can go ahead and minimize this, right. So, a couple of things which I want to point out now. So, one thing is, if you notice the penalty here, so what do you notice about this?
Whenever it is larger than 0, we are penalty.
No. I am not including beta naught, right. See, the sum runs from 1 to p, it is not running from 0 to p. Also note that I actually explicitly wrote out beta naught here, I did not squish it into the p plus 1 thingy, because I am going to be treating beta naught specially here, mainly because if I penalize beta naught, then what will happen is, if I move my data up, right. Okay. So, let us say this is my x and y axis, and I have, this is the data that I had, right. So, now I have to fit a line through this, right. So, the x I have, it's a univariate regression problem, y is my response and x is my input, I have to fit a line, right. But now the same data points, okay, if I shift them up, right. So, shifting up the data points is hard, so I will just shift the origin, okay. If I shift the origin, what will happen if I penalize beta naught? No. So, if I penalize beta naught, it will try to keep this intercept small, right. penalizing beta naught will try to keep the intercept small. So earlier when I had that, right, if you look at the fit it will pass very close to the origin, the intercept will be close to 0, right. Now when I have shifted this, it is going to try and make the intercept small. Instead of the line just shifting, the slope of the line will change, right. It is the same data, it has just shifted up a little bit, right. So the slope of the line will change, so it will try to go through somewhere here. So essentially earlier when the line would have been like this, right, now the line will become like that because I am penalizing beta naught, right. So we do not want that to happen, so just simple shifts in the data should not change the fits, right. So we do not penalize beta naught. Right, does that make sense? Okay. And anyway we know what beta naught should be. Do you know what beta naught should be? Right, it should be the average of the outputs anyway. So one way which we can actually get rid of beta naught from this optimization problem is to say that we will center the inputs, right. So we will subtract the average from the yi's, and likewise we will subtract the averages from all the x's, okay. So we will center the input, so we will make all the x variables centered on 0, right. So we will subtract the mean from all the x's, we will subtract the mean from the y's, okay. So this will give me a centered input, okay, and then I will just do regression on this centered input where there will be no beta naught, okay. So from now on when I write x, it is a n cross p matrix where the input has been centered, okay. So that way I do not have to worry about the, so essentially what I have done here is I have taken my data from there, okay, and shifted it so that the fit, whatever is the fit I am going to get will pass through the origin, right. So that is essentially what I have done, I have taken the original data, translated it so that whatever I fit will pass through the origin, okay, and I will go back and add the beta naught later to get the original fit. Does that make sense? People are fine? Okay, good. So in matrix form, I write it like this. So you can minimize this, take the derivative, set it to 0, solve for it, you will get this. So here, so both my x and y are centered. So I have subtracted the mean from y, I have subtracted the mean from the columns of x. So they are all centered here, okay. So just remember that, and so once I get the centered values I can solve for it. This gives me the beta hat ridge for 1 to p, right, and the beta naught I estimate as y bar, and that gives me the full solution, okay. Is that fine? So one thing which I forgot to point out earlier, you remember I had this variable t here, there was upper bound on the, so I said subject to the constraint that it should not be larger than t. The t has vanished here, but you can show that this lambda and the t are related, right. So it does not matter. So for every choice of t you have a choice of lambda, okay, but typically what happens is you choose a appropriate lambda and then you work with it, you do not worry about the t formulation, okay. Any questions on this? So this tells you why this is called ridge regression, because what I have done here is you have essentially added a ridge to your data matrix. You take the x transpose x, okay, and then you add a diagonal lambda to it. It is like adding a ridge of size lambda to the diagonal elements of x transpose x. Okay, that is why it is called ridge regression. So why are you doing this? I mean, can you see one advantage of doing this lambda I thing here? Sorry? This whole thing becomes invertible, right? So as soon as I add the lambda I am sure that this is non-singular. Even if x transpose x was originally singular, right, adding lambda I makes it non-singular and it is invertible. In fact, this was the original motivation for ridge regression, right? Back in the I forget when, the 50s, when people came up with ridge regression, the original motivation was, hey, x transpose x could be badly conditioned, okay, even if it is non-singular. We talked about this in the last class, right? It could be that some variables are so highly correlated, so even if the matrix is invertible, numerically you will get into problems, right? I told you that the residual might be so small, right? So when you try to fit the coefficients, you will get into problems. So numerically the inversion might be a problem, right, even if the matrix is non-singular. But by adding this lambda I term to it, you make sure that it is invertible, and by controlling the size of the lambda, you can make sure that numerically also the problem is well behaved, right. So that is the idea behind original motivation for ridge regression was essentially to make the problem first of all solvable, right. But then people went back and understood ridge regression in terms of shrinkage or variance reduction, and since it makes it convenient for us to talk about a whole class of problems, shrinkage problems, right. So we motivate the motivate ridge regression from the viewpoint of shrinkage as opposed to this inversion problem, right. Any questions? So I am going to encourage you to read the discussion that follows ridge regression in the book. Okay. It requires you to work out some things along with the book. You just can't just sit there and passively read it, okay. But then it draws a lot more connections from ridge regression to variety of other statistical properties about the data, which will be useful to know, and I am going to make you read. I mean, so go read it, right. I might ask you questions on it later. So go and read the discussion, okay. So the next thing